In chapter 4, I'm going to talk about some of these ideas of aqueous solutions and some of the terminology that we use when we're talking about aqueous solutions. One of the things that we kind of think about here is to use baking as an analogy. We don't typically just mix dry ingredients together and throw them in the oven. We're typically adding eggs and milk or water and mixing those things together because it allows some of the molecules to interact with each other better. There's a mixing that happens more efficiently when you make things wet. So that's why water is so important in life and why water is so important for chemistry. So we think about water, and 60% of the human body is water, and some of the ideas that we will be talking about is how water dissolves ionic compounds. We're going to talk about ionic compounds and what those mean and what those are. We're also going to dive into a little bit of a discussion about acid and base reactions that occur in water. So when we're talking about reactions in solution, different products need to make physical contact in order for the chemical reactions to occur. So in the gas or liquid phase, this is allowed. This can happen. Gases can react all the time easily because there's easy mixing between those reagents. This is also true in liquid. Less true for dry chemicals, although there are some chemical reactions that can occur if you're just mixing dry chemicals together. So this is where some of the terms come again, where we talk about homogeneous mixtures, where they are mixed completely and it looks like one complex group is that the mixture is similar throughout. And that means that the molecules and ions are completely intermingled, and it also means that we have at least two substances within our mixture. And when we're talking about the solvent versus the solute, here's just a term that you should know, some different vocab words. The solvent is the thing that the solute is dissolved in. So the solvent is typically going to be water. Not always, but most of the time the solvent is going to be water, and the solute is the thing that's dissolved in the water. It could be a salt, it could be an acid, it could be a base, it could be sugar, it could be a molecule, it could be a lot of different things. But typically, for the most part, a lot of times, the solvent is going to be water. All right, so I want you to think about if we have a cup of coffee, it has milk and sugar, which of these are the solutes? Which are the solvents? So take a guess at this and post in the Blackboard space, and then we'll have a conversation about this later. So a few more vocab words to talk about when we're talking about water solutions. Concentration. We want to have a discussion about this, and here remember we talked about the solvent. It's typically water, so let's pretend these blue beads here are kind of molecules of water, and the red circles here or spheres are the solute. So it could be something like sodium chloride, for example. We have dilute solutions where we just have a little bit of that solute involved in it, and then we also have concentrated solutions where this has a lot of the solute dissolved and potentially to the point where it's almost overly saturated. So saturated solution basically says that we have as much solute as we can get in there, and really what this means is that the solvent is able to kind of surround this molecule fully to keep it dissolved in solution. As soon as there's too much solute and the solvent can't encircle it and contain it, it'll start to fall out of solution, and that's oversaturated. And that means that we've put too much of our solute into our solvent to dissolve. Unsaturated solutions or dilute solutions where there's plenty of solvent to dissolve the solute in. So basically you have to have so many touch points for the solvent. It has to be able to surround the solute. Otherwise, if you don't have enough, then this starts to fall out of solution because you don't have enough of those interactions between the solvent and the solute to keep it dissolved in your solution. Solubility is going to be different depending on the solvent and the type of compound that's being dissolved in that solvent. And so a lot of times this equation is used in order for people to report out and tell us how soluble certain compounds are in various solvents. And the way that this is done is basically you look at the number of grams of a solute needed to make a saturated solution over 100 grams of the solvent. And this is always temperature dependent, which is interesting because when I went back on this other slide, remember we talked about these solvent molecules being able to dissolve this. The warmer the temperature is, the actually more of this that the solvent is able to move around and shake and touch and bump into the solute and dissolve it. As soon as the water, for example, if this is water, if it cools, it stops moving around as quickly, it stops shaking as much, and there are less interactions. So you can think of a really hot water molecule that'd be bouncing around and it'd be hitting all these solute molecules, and that keeps those in solution. And if we cool off the solution, then these start to move around slower and have less and more slow interactions, and they can't hold as much of the solute in solution, so that the solution then will become oversaturated, and a lot of times this will fall out of solution. So these are temperature dependent because those interactions between the solvent and the solute are really important. So just to look at this as an example, here's some solubility chart looking at sodium chloride, for example, in water, in 100 grams of water. At 0 degrees, you can only get 35.7 grams of sodium chloride in, but you can bump that up to 39 if it's closer to boiling. So we get almost 4 extra grams of sodium chloride with a 100-degree temperature bump. Sodium hydroxide, we have 42 at 0 degrees, huge jump, nearly 300 extra grams when we increase that 100 degrees Celsius. And calcium carbonate, we really don't have, the solubility is very, very, very low. So this is generally a very low to non-soluble salt in our solution here. You may have at one point either tried to make these kind of these sugar candy with using supersaturated sugar solutions, or maybe you've just eaten it before, but basically you boil sugar water and you can get, again, kind of like this idea where with sodium hydroxide you get a ton of those grams of sugar, for example, not sodium hydroxide, hopefully, sugar in solution at boiling, and then you cool it down. And then what happens if you do this slow enough and in a controlled environment, though, that sugar, for example, with its rock candy, these will start to crystallize on the stick, and then you form these rock candy sticks. So that's basically how supersaturated solutions can work. And then this allows the clean precipitation and the organization of those sugar crystals, for example, onto the stick here. So next we're going to talk about precipitates. So that's kind of this same idea. When things start to fall out of solution or crystallize, that means that they are not soluble or lower solubility than what the temperature or the conditions or the concentrations are at. So sometimes different chemical reactions, we will form products with low solubility and they will precipitate out of solution. So here's an example of a precipitation reaction where we have lead nitrate. This is aqueous, which means it's soluble currently in water. So this AQ is aqueous, it's Latin for water, plus 2 units of potassium iodide, and that is also aqueous. So these solutions here, lead nitrate, potassium iodide, you can see here, they are clear solutions, which means that they are homogeneous solutions where everything's solubilized in solution. These react to generate lead iodide. This is a solid substance. That means that it is going to precipitate. It's no longer aqueous, which means it fell out of solution. And it also will generate 2 units of potassium nitrate, and this is aqueous. So this tells us that we have 2 soluble solutions, we mix those together, and then generate 1 precipitated solid compound, which is lead iodide, and then it has another group here that is still aqueous. So we'll talk about these, what these are called, and how to look at understanding chemical reactions like this. So we're going to start with looking at breaking these components down and rearranging them into their new groups. So that's kind of the first step here in this type of reaction. And then we're going to need to identify which things are falling out of solution and which are precipitating. So based on what I just told you, there's some certain things that I focused on to tell us about the solubility that was happening in that last problem. So you should be able to, based off of that, determine which of these compounds in this reaction are have precipitated, which have fallen out of solution. So post your answer in Blackboard, and then we'll move to the next set of slides. Just briefly before we get into more ionic compounds in water, I just want to talk about molecular compounds in water. So if we have sugar, I've brought this up a few times, giving sugar as an example of a molecular compound. These molecular compounds don't fall apart and don't form ions like ionic compounds do. They stay together. Some of them can still be water soluble, and we'll talk about how that works later in this semester. But right now what we need to know is that these can fall apart and be dissolved in water. Just like this is showing, right? We have multiple water molecules surrounding the sugar, so sugar can be dissolved in water. And we can see that this is kind of the molecular structure and makeup of water, and we have carbons at the edges, but this doesn't fall apart. These don't break apart and disassemble the units like we do in ionic compounds. This is an example of an ionic compound where we have sodium, the sodium in blue and the chloride in green. We actually have electrons have moved over from the sodium to the chloride, and so we have positive and negative compounds, and these are broken apart, right? The sodium and the chloride are 2 separate groups that break apart and dissolve in the water. And these are interacting differently than the sugar molecules because the sugar molecules are taken up whole, and these sodium chloride molecules are kind of taken apart and dissolved in the water. So just a note, polyatomic ions, those polyatomic components, those do stay together as groups, as charged groups together. So that's a little different than what we're talking about or more similar to molecular compounds. But the difference there is that they actually have a charge contained on them. Examples, potassium iodate. These are going to fall apart into potassium ion and then iodate ion. So this is a polyatomic. It's a group with iodine and 3 oxygen molecules that actually take on a negative charge. So those will stay together, and we'll give you some more examples of that in just a moment. I already talked about this earlier in the semester in an earlier chapter, but ionic compounds conduct electricity because they're charged, they have ions. We have the ability for basically what's happening when we have conduction of electricity. There are electrons that flow through this light bulb, through the solution to connect these the battery, for example. And copper sulfate and water will conduct electricity. Sugar and water does not. Again, because of this idea that I showed you before, when we have solid compounds that, like sugar, dissolved in water, there is no ion, there's no electron spot for this to move on. Where there is a positively charged group where electrons can flow if this is concentrated enough. So why, again, this is the copper sulfate, an example of these positively charged copper ions. Electrons can flow through these positively charged groups and then from one of these electrodes to the other. So they have a pathway between these electrodes through the copper, the solubilized copper in this solution. Would you think, based off of what I just talked about, how this works, how electricity flows, Would it flow better through a dilute solution of copper sulfate or through a more concentrated solution of copper sulfate? And why do you think, based off of your answer, what you're thinking, what your hypothesis is, why do you think that? What is the reason? So post that on Blackboard and move to the next slides here. Most molecular compounds are non-electrolytes, and you can see here this is an image of sugar on the left, alcohol on the right. These don't break apart, certainly not as easily, and so we don't see any ions formed. We don't see positive or negative charges on these, and because of that, that positive charge, what that means is that an electron left and it went somewhere else. And when that has a positive charge on it, remember that last slide, we were looking at these electrons can jump on to compounds with positive charges. So if there's no positive charge within that compound, then the electrons can't jump and flow through it to get across to the electrode in the sample here. Generally, molecular compounds do not conduct electricity. All right, so now I want you to think about how many ions form when the following compound dissociates. So think about what is happening when sodium and the phosphate break down. And also, I want you to make sure that you remember that when we're talking about phosphate, one of those things you need to start to be able to do is to identify various polyatomics. So that is going to be a polyatomic, and we can use that sheet where on that other slide where we basically had lists of polyatomics. To solve this problem, remember we need to do the crisscross and in order to figure out what the charges are for each compound. So sodium, because there's no number down here, it's an inferred one. And we always have the positive ion first. The cation is always first, and then the anion is always second. So we have PO4, and it's going to be a -3 because that's what that subscript is. So in order to cancel these charges out, we have a -3 charge right now on the phosphate, a positive charge. This wouldn't be an equal ion, right? We'd have an overall -2 if we just had a 1-to-1 ratio. But this number, this subscript, tells us we actually have 3 sodium ions. We just have 1 phosphate. That gives us a +3 charge when we're talking about how many charges, because we have 3 of these positive charges and just 1 negative charge. So it's a -3 and a +3. The overall charge is 0. So we actually have 3 + 1 is 4 total ions that this compound consists of. So I'd like you to take a moment to do that same thing with now aluminum sulfate and just tell me, basically show me what is the ion charge for each group and then how many of each of them are there, and post that in our Blackboard space. I mentioned during the learning check that most molecular compounds do not ionize, and that's not always true. So there are differences. This is a salt, so we have hydrochloric acid. HCl is it strongly breaks down into H plus and Cl minus, and in here it's shown as H3O. So it basically, the positively charged proton attaches to the oxygen. But this is a strong electrolyte because it breaks apart very easily. Now, molecular compounds don't break down very easily, but sometimes they can, and certain weak acids are sometimes made from molecular compounds. So here's an example of C2H4O2, and some of those hydrogens can break off into an acid form and leave ions charged. But this is a really weak electrolyte, so it doesn't happen very frequently and very commonly. So you can see that there's a little bit here, and then the charge is, or you can see that the electron flow can come through here a little bit. And then there are others that are really, really weak and don't happen very much at all. And so that is another one. Here's ammonia. Once in a while it'll happen, but very infrequently as well. So weak electrolytes versus strong electrolytes, same kind of concept as a very concentrated salt solution versus weak. the more concentrated your positively charged ions within your solution, the more those electrons can easily flow through that across the liquid to your electrodes. So I'm going to come back to that, the learning check again, to write the equations that will illustrate the dissociation of the following salts. So it's the same concept. We're going to break those down. We use the crisscross rule. We need to identify polyatomics like this phosphate, and we're going to break those apart into those groups. Just like we did last time, we want these to be balanced. So we have 3 sodium phosphate or sodium salt compounds and then phosphate, and then we have the aqueous solution here, so these are in the aqueous form. So do that for the other 3, and then we will we'll move on to the next couple of slides. So post this in the Blackboard space. Next, we're going to talk about the different ways that we can write equations and for aqueous solutions, and these are going to be useful in different situations. So let's start with just kind of defining these. First, we talk about the molecular equation, and we will list this lists the whole complete formula. Ionic equations, however, separate those things out, and they're broken into ions, just like we did on that last learning check. Rather than having those compounds together, they're broken apart into the ionic forms, like we were shown in that last slide. The net ionic equation only lists the substances that actually take part in the reaction that cause a precipitation or there's some type of gas creation. So we'll talk about that. Let's look at these different examples and show you the difference between them. So if we're looking at this following equation, we have lead nitrate with potassium iodide, and we can break these apart into their ions that they're forming, and then the lead iodide is a solid. So these are the reactants. This is the product. And let's look at some of the different ways that we can write this with those various equation formats I showed you in the last slide. So the molecular equation doesn't indicate charges. It doesn't directly show you that. It gives you the identity of the compounds, and it's good for planning experiments. So I'm going to take lead nitrate, I'm going to get the salt off the shelf, potassium iodide salt, I'm going to mix these together in water, and then see what happens. So you notice these are all together. We do tell you if they are soluble or not soluble, soluble, these are all soluble. So this is an example of the molecular equation with that example. Ionic equations emphasize the ions that are forming. And we're going to, insoluble compounds are written together. So here we're breaking these apart. So it's kind of like that learning check we did where we break all of those ions apart. We're showing you how many of the ions. So right, 2 nitrate ions, 1 lead ion with the certain specific charges are defined up in the upper right hand corner, react to form solid lead iodide. And then these are going to be the aqueous salt products. So this breaks down things, and they're really to help appreciate the context and what things are involved. Now the net ionic equation, this is the ionic equation. The net ionic equation eliminates the spectator ions. So in here we have the lead and the iodide. Those are the things that actually formed the solid here. Those came together and formed the solid. And what we did is we canceled all of the ions that didn't do anything on both sides of the arrow. So that 2 nitrate ions, they didn't do anything. They're still nitrate ions in solution. There is no function besides to act as the initial salt. The potassium ions, those did not do anything necessarily in that reaction. So those were eliminated from the net ionic equation. When we're looking at equations that involve ionic reactions, we need to make sure we have a couple of things taken care of. We've already practiced balancing the atoms in the materials, and those, we need a material balance. So we need the same number of atoms on the right and the left side of the arrow. We also need to have electrical balance. So that means that we don't necessarily have to have a zero charge. The charges don't have to cancel out to be zero. But if you have a negative charge on the left side, a -2 charge on the left side, you need to end up with a -2 charge on the right side as well. Remember, charges are electrons, and it's the same. An electron is matter. So you can't eliminate matter, you can't create matter in a reaction. So that has to be an enclosed system. We have to account for the electrons. So you have to have a balanced electrical charge. They have to equal the same thing on both sides. So this example, if we have a +2 charge on for one compound and a -6, the overall is going to be a -4, right? And then we have a +4 and a -8, so the overall is a -4. So this is okay. This is an okay example. If those charges were present, we start with -4, we end with -4. That accounts for all of the electrons. So we need the atoms to be the same, and we need the electrons or the electrical balance to also be the same. So with that in mind, I want you to look through these 5 different equations, and I want you to tell me which one of the following is not electrically balanced. So define which one's not electrically balanced, and then we're going to move to the next slide here. And I'd like you to post that answer in our Blackboard space and describe why do you think it's not balanced, or what would you do to fix that problem. Ultimately, the reason we're going to mix things together is to get a product out. And just as an example, there are many different ways to make lead iodide. So here we have, for example, we could start with lead nitrate and or lead acetate and potassium iodide, ammonium iodide. We can still, for both reactions, we're going to make the lead iodide the solid salt solution, solid compound solution. That's not going to be soluble. Remember, these come together and they form a solid because they have low solubility in water. Those are the parameters of that compound. They just have a low solubility. So anytime lead and iodide ions come together, they're going to fall out of solution because of their low solubility. Potassium nitrate, ammonium acetate, however, these compounds are still aqueous. They're still in solution. So we have different starting solutions, but we have the same net ionic equation, because if we were to break these down into their ions, we would have the nitrate ion on both sides of the equation. We'd have the potassium on both sides. They wouldn't be doing anything. So the net ionic equation just tells us we have different ways. It doesn't really matter what salt, what other anion you would use for this compound or what cation you'd use for this compound. These are the things that are going to come together to be a solid compound. Those other compounds are just going to be spectator ions. If we want to convert molecular equations to ionic equations, to some extent we've already been doing this, but here's just a strategy to make sure that you know how to do it, or you have steps in order for doing that. First, you want to identify strong electrolytes, so salts that have compounds in 1A and 2A columns of the periodic table, so those first tall columns of the periodic table, and then the ones on the other side, not probably the noble gases are not going to generally be involved in ionic equations, so you won't have to worry about that. But these 6A and 7A, these compounds, those are on the right side, right columns of the periodic table. Those are going to generally break apart really well. You'll want to use the subscripts and the coefficients to determine the total number and each type of ion. And then doing the crisscross rule, kind of going backwards on that to determine the charge. Then separate all of the ions with all the strong electrolytes, and then show states as recorded in the molecular equation. So make sure that we still have, if it was aqueous, it's aqueous. If it's a solid, it's a solid. So continue to do that. So here's an example of lead nitrate and ammonium iodate. And we're going to have this is going to form lead iodate, and we have ammonium nitrate. So I'm going to break all of these apart. So we're going to make this is aqueous. So we know that breaks down into a charged compound. This breaks down. You'll have to recognize, again, some of the polyatomic ions here. I know that NH4 is one and IO3 is one. And then this is solid, so we are not going to break this apart, but we break this ammonium and the nitrate down as well on the right side. One of the other things you can do to figure out, since this is the other side of the equation, we have an IO3 over here. Well, that gives you a hint that that's a grouping. And then that means if we're looking especially at ionic compounds, probably the other thing in there is also a polyatomic. So that gives us a hint that, oh, this NH4, and then you also see it down here. The NO3 was bracketed for you, and you could see that down there. So you can without having to go to a chart a lot of times, you can identify the polyatomics based off of where they're moving in the reaction equation. So here we have Pb plus 2. I got that positive 2 by looking at that subscript on the other side of this anion. So the cation plus 2, we do the uncrisscross. That lead has just a inferred 1, so that's going to be a negative 1 on the nitrate. We have the 2 of these compounds. NH4 is one grouping, IO3 is another compound. This subscript isn't part of the charge here, right, because it's in brackets on this one, so we know this whole grouping, this whole IO3 group is going to be a polyatomic, and this whole NH4 group is also polyatomic. This just says we have 2 of them. So then when we break those apart, for example, we're getting the right number. So remember also we have 2 of these. There are 2, so we need to make sure we write that 2 out as well. NH4, we are going to break that down. That's a positive 1 because there's an inferred 1 here and an inferred 1 here. So the iodate, we have a negative value here when we do the uncrisscross. And that 2 in the front tells us that we have to have 2 of those compounds each. On the other side, the lead iodate doesn't get broken apart because it's still solid. And we've written that as well, that state here. And then the NH4 and the NO3, those are polyatomics as well. And we have inferred 1, so those will have a positive and negative 1 respectively. Also, we have that 2 in front, so we need to make sure that we have 2 of those ions that are represented. So that is how we generate an ionic equation. Now, I'm going to give you a chance to write out the correct ionic equation to be one of these examples for the following. So just make sure that you identify the ionic equation. There might be a net ionic equation in here as well. So identify those and post your answers in our discussion board space. Now I'd like to talk to you about, we have been looking at ionic equations. I want to talk about converting the ionic equations to net ionic equations. And we look at, first we need to identify the spectator ions. So the ions that are just spectating, they're not doing anything, they're there and they are on both sides. So we're going to go look at some examples of this. Here's an example of an ionic equation. We have lead nitrate, potassium iodate, and then we form this solid lead iodate compound with an S on it. All of the other compounds have aqueous behind them, which means that they're dissolved in the water solution. Now, I can identify a few nitrate here, nitrate, potassium on both sides of this arrow. Now, I've obviously dropped this down because this whole thing doesn't fit very well if you want to see. But here I've canceled out similar compounds on both sides of the arrow. And now I just write down the things that were not canceled out. The lead, aqueous lead ion, the 2 iodate ions, and then react to form this solid compound. So that's how you do it for generating the net ionic equations. So now I'd like you to try to create a net ionic equation, again, following the previous example as a guide, and practice and post your net ionic equation in our Blackboard weekly discussion space. Now I just want to walk through some of the ideas for balancing ionic equations and some of the considerations that we need to make when we're doing this. Remember, we need to make sure we're balancing the material, so the atoms involved, and we're also balancing the electrical charge. So we need to have the same number of atoms and the same overall charge. Again, it doesn't have to be 0. We just need to make sure that the charge is the same on both sides. Otherwise, that would mean that we're changing the number of electrons that are found in the compounds. So let's start looking at some of these things and thinking about how we can start to predict if a compound is going to be soluble or insoluble. And that comes to this idea of these solubility rules. So what we're really doing is kind of a do-si-do of these two different compounds. So we see that the lead and the nitrate just basically switch partners with the potassium and the iodine. So we have the lead is moving with the cation, is moving to the anion. They're switching partners here. And that's essentially what's happening. And we have this is precipitating out. So what we're going to do is I want to look at a chart here that's going to tell us something about solubility. So you might see different ones, or you'll be able to find different ones online. But these essentially here on the top are going to be the anions, the negatively charged ions. Here we have like chloride, bromide, iodide. Then we have polyatomics here, carbonate, hydroxide, common nitrate. We've seen some of these previously. We also have sulfide, oxide, various other compounds as well. Now, these are going to be the negatively charged, and on this column, we're going to have the positive charged cations, lithium, sodium, and then as we get down, there aren't very many, you'll notice, cation polyatomics besides ammonium as well. So the only other one we might see in here, which I don't actually have listed in this one, would be mercury. So these are some examples of various compounds that we might see that we might mix together. So if we're mixing beryllium and hydroxide, what's going to happen? Is it going to be soluble, non-soluble? So you can do this every time you mix these together. You'll have an idea, and this chart basically tells us what is happening. So this, for the key for this is, and you might see this in different states, maybe you'll see an AQ or you'll see solid. This actually can be somewhat confusing, but the S here isn't solid, it's actually soluble. So an S in this instance is soluble, and I is insoluble. SS is slightly soluble, and then you might have different where you'll have an X would mean other, so sometimes it works, sometimes it depends on the situation, the acidity perhaps. R means it reacts with water, so you wouldn't put those things in water because it's unreactive. Question marks would be unavailable, or you can't react this with water because for some other reason. So some of these, for example, they're water reactive, so we don't have data for that, or it's going to interact with the water and cause a secondary reaction. So this is a general solubility key, and you'll notice there are certain trends. Like silver tends to be insoluble in a lot of different compounds. Carbonate's also insoluble. Sulfide's always insoluble. So there are some different trends you might see. And you notice most of the time acetates are highly soluble, and chlorates and nitrates, sulfates for the most part. So there are some things that you'll notice, ammonia typically, with some exceptions. So here's just some solubility chart. You might want to screenshot this or look at this to have a picture of this, or have a website with solubility charts when we're looking at some of these, so that you can use this to identify or to predict if something is going to be soluble in a certain chemical reaction involving ions. Okay, so what we want to do is just kind of make sure that we understand that image that I just showed you with the solubility chart here and how to read it. We will look at which of the following compounds would be expected to be soluble in water. So you'll have to go back and check that list and cross-reference it with this one. Basically, we mentioned a lot of these compounds. The acetate are generally always soluble, so that one is. Iron carbonate, you basically come over here and carbonate. Nope, this is an insoluble. And then finally, silver chloride. We are going to move back here. And I mentioned most silvers are insoluble, and with chloride, it's insoluble. So, yes, no, and no according to that. So that's how you would use that chart to determine if something, and then if this were kind of your chemical reaction, remember we'd have solid and S in that state, and generally anything else that, if it were soluble, it would be AQ for aqueous. When we do these metathesis or double replacement reactions, there's only a chemical reaction if a couple of things happen. So if we're just putting something in solution, we mix two different salts together, there's no reaction if they're just mixed together in the mixing container. But if we have something where a solid forms, so a precipitation, a gas is formed and leaves the liquid, an electrolyte forms, or a non-electrolyte product forms, and I'll talk about what that means in a second. But if any of those happen, then we're going to talk about a chemical reaction is created. So let's go through some examples to describe that in a little more detail. So first of all, let's take HCl and CaOH2, hydrochloric acid and calcium hydroxide. We're going to basically identify which are going to be the ions. So it is the cation and the anion, and then we're going to swap them around. Make sure that you're keeping track of the subscripts and how many of each of the ions that you have present. We need to determine if there's going to be some type of driving force or the formation of a weak electrolyte, non-electrolyte, gas or solid, or water formed. So here, let's look at this example. We're going to break these down into their various ions. So we have H plus, Cl minus, Ca plus 2. Remember, we do the anti-crisscross rule. So the calcium plus 2, so that we have a balance of the charges, and 2 hydroxide ions. So now we're going to swap these out. We're going to swap the cations and anions with the other partner, and we're going to get calcium chloride, CaCl2. Remember crisscross, so we have 2 of these. And then we have HOH. That's also H2O. So if we have HOH, that's going to be H2O. We're going to form water. So that is going to be a driving force. This is going to be, actually, you put an L back here for liquid, water, and this is going to be a chemical reaction that moves forward because we're generating water. So that was an example of water formation. So an overview, we get precipitation. If you get 2 solutions and then you form a solid product, that is going to be a chemical reaction through a metathesis. If we were going to have neutralization, so if we take an acid and a base and we generate water, like we did in the last example, that is going to be a chemical reaction. Gas forming. So some of the possibilities, and this would be where you would have to know this, or I would give you a list and say, hey, look out for these. These are actually gas forming. So if they come together, you generate HCN or H2S, H2CO3, H2SO3, NH4OH. These are all different compounds that will actually decompose and end up forming gases in the end. But I would, if they were on the quiz or something, I would let you know, hey, look for these, or I'd put them on the front end and just say if these come up, just know that these are going to be gas forming compounds that will decompose into gases. All right, so here's an example. I want you to determine, looking at these compounds, do a metathesis, synthesis with them, what are the products, and then will there be a solid product form based on the solubility chart. So post that if there is a solid that's formed, let me know, or if there's some other force that's going to drive the reaction, let me know what that is. Just another learning check here. I would like you to do the same thing, do the metathesis, determine if there are any products, and if there are products, let me know what it is and why it is going to be a driving force here. Now I want you to kind of think back and kind of put this all together, use all the vocab that we've kind of picked up over the course of this lecture, and I want you to look at this compound where we have a cadmium nitrate and sodium sulfide. I want you to mix those together. I want you to predict the products, and I want you to write down the molecular ionic and net ionic equations based on everything that we've talked about. Post your answers for those 3 forms in our Blackboard space, and then we'll move forward with the rest of the slides here. So again, just a few more, an overview and a few more problems since we talked about this, but we're really looking at driving force, something to create either a precipitation product, neutralization, some type of gas, or the formation, for example, of a water or a different type of electrolyte. So these are some of the things that will drive these metathesis reactions. Otherwise, if these are not happening, everything's just soluble and there's no reaction. So that concludes this part of the lecture, and look forward to our next discussion.